morning, everyone, and welcome to another edition of Microchip Live. I'm Dana Curtis, and I'll be your host for today's discussion. We have a fascinating topic that affects each and every one of us, the increasing demand for electricity in our daily lives. From the moment we wake up and check our smartphones to the time we turn off the lights at night, electricity is the invisible force that powers our modern existence. Our homes, workplaces, and even our modes of transportation are becoming more reliant on electrical power. With the rise of smart homes, electric vehicles, and the ever-growing number of electronic devices, our need for electricity is skyrocketing. But this surge in demand brings with it a host of challenges. Our current infrastructure is being pushed to its limits, and the environmental impact of traditional energy sources is a growing concern. How do we balance our increasing appetite for electricity with the need for sustainability and reliability? To help us navigate these complex issues, we have three distinguished guests with us today. First, at the other end of the desk, we have Jason Chang, Product Marketing Manager here at Microchip. Jason will provide us with a comprehensive overview of where we stand today, the challenges we face, and the potential risks if we don't adapt to our growing needs. Next to him, we have Steve Chenitz, Senior Technical Staff Engineer at Microchip. Steve will introduce us to one of many unique solutions involving silicon carbide, which provides the capability for us to take advantage of this future electrification of everything. And to my left, we have a very special guest from Tektronix, Cameron Lowe. Cameron is a field applications engineer who will provide commentary and some objective insight into the viability of these solutions. I'd also like to introduce our marketing specialist, Allison Brown, who will act as our Q&A moderator today. Allison will be monitoring the chat feeds throughout the live stream. Allison, what can our viewers expect today?
Thanks, Dana. Good morning, everyone. Thank you for joining us live on YouTube, LinkedIn, and Facebook. I'll be monitoring the chat throughout, like Dana said, so if you have a question that comes up during our broadcast, please feel free to leave it in the comments or chat. We'll try to get to it at the end. And if you're not watching live or you have a question that comes up later, you can always shoot us an email to livestream@microchip.com, and we'll try to get back to you there. So I'll see you back at the end for some questions.
Thanks, Allison. Throughout the show, we'll discuss key questions such as what are the most significant factors driving the increase in electricity demand? How can we upgrade our infrastructure to handle this surge? What role will Microchip technology play in our future? And perhaps most importantly, how can we ensure that our energy solutions are both sustainable and accessible to all? So I'd like to kick things off with Jason. What can you tell us about the electrification of everything?
Well, I'm going to start off with the role of silicon carbide. It's going to be quite relevant, as was showed here today, in the electrification of everything, because it's all about the increase in power fidelity. As Microchip talks about the electrification of everything. It's all by markets. Key market trends the audience will be familiar with are e-mobility, like including automotive and transportation applications, 5G, as well as AI-driven data centers. That's the new trend nowadays. There's A&D, aerospace and defense applications. There's also a lot of applications over in the industrial sectors, maritime, and many other energy sectors that are quite important in electrification of everything. Everything's moving away from fossil fuels, improving the carbon footprint, and the process of doing so, driving more of the electric generation demand, as well as the way of storing this electricity. All this translates to switching efficiency, and we'll take a look at how some of those areas affects the lifestyles of our audiences. One prime example, you might be familiar with solid-state circuit breakers. It spans across all the application megatrends that I mentioned earlier, because primarily it's all about circuit protection. You have battery power systems, you have DC grid supplying into your electrification applications. All this needs circuit protection, and with silicon carbide, for example, it's all about protecting the circuits at 100 to 500 times faster than existing electromechanical solutions today. As an example, interesting enough, there's a recent ABB paper I read that cites that in maritime vessels, for example, depending on type of ships, a DC circuit protection with circuit breakers can potentially save up to 70% energy use. That's significant, preventing that much power loss. And over a 10-year period, depending on the ship again, anywhere from $200,000 to $1 million savings for the operators. That's significant for use of silicon carbide in such power applications. And now another great application, and we hear about it daily, with all the artificial intelligence, the AI-driven applications, is driving huge data center demand. Now, data centers obviously been trying to go have a smaller footprint, run cooler, to be greener, quote unquote, to be friendlier to the environment. Well, AI-driven applications is having the opposite effect. What it's actually doing is increasing demand by 30–40% at data centers, primarily because, for example, ChatGPT, for example, take one query. I believe I read in a recent ABB paper that one query could be equivalent to 100 carbon footprint of just one simple Google query. Now multiply that by up to 10 million, for example, queries a day. About estimated gigawatt power can power easily over 30,000 households. So you can see that 10 times that for a single, what they call large language models or LLMs, and that in addition times X amount of LLMs, that's greater than 10 gigawatts of power a day. Now, that's a significant increase from the current demand of data center use today, causing huge bottlenecks not only in GPU, CPU, computing power, but also in energy storage, and all that translates to power usage. And that's where Microchip's role is there, is helping with the power supply delivery into these data centers. Now there are many other sectors. Steve and Cameron here also have quite experience. I'd like to turn to Steve, for example, to perhaps cite another example from his experience.
Yeah, it's estimated in the next 25 years that just due to EV charging alone, the usage for electric will increase by 50% over what's being delivered and generated right now. That's a huge increase in electric usage, and there's a real need to improve the efficiency from generation to power, transmission, delivery, and usage. And silicon carbide can play a role in this kind of improvement in efficiency.
Yeah, speaking of EV charging, another sort of offshoot from the electric vehicle market is what we would call heavy-duty vehicles or off-highway vehicle manufacturing. This is another area where wide bandgap type of devices such as silicon carbide are being adopted. Challenges there include, all the same challenges that you would have from electric vehicle development, but a lot of these vehicles require huge amounts of load current delivered in a short period of time. So heat dissipation is very important, and testing these types of products over varying load conditions is also very important. From a defense and aerospace perspective, you're also seeing an adoption of silicon carbide and wide bandgap materials in those types of products. Examples would include in the aerospace market, commercial aircraft, not adopting an all-electric aircraft type of model, but more of supplementing some of the subsystems with electric components. Again, all striving towards higher efficiency, longer flights, using less amounts of aircraft fuel. From a ground perspective, defense vehicles such as four-wheelers and tanks are also developing electrification, and some of the concerns there are obviously these are mission-critical products. These are devices that need to be tested over a huge variety of different conditions, not only in terms of their efficiency and what they can deliver from a power perspective, but what sort of interference they may have with the other components on board, say, like a forward operating base or a ground vehicle. So all of these kind of point back to both challenges, but potential improvements that might be added to markets outside of what we would traditionally think from an electrification perspective.
Yeah, improving efficiency is an ideal role for silicon carbide, especially when we talk about silicon carbide replacing existing technologies such as silicon or even IGBTs. As we move to higher power, much higher voltages, we need a device that can not only reduce the overall system size, but improve the efficiency and also reduce power dissipation, giving us a lighter, smaller, more efficient, compact solution.
Yeah, and some of the other considerations to keep in mind with silicon carbide are the higher switching frequencies and the higher rates of switching these devices on and off. That can lead to challenges in the EMI space or the common mode testing space, where now similar to the challenges that the automotive manufacturers had back when FM radios were kind of first introduced, considerations in terms of how these power supplies and converters and inverters are affecting other Wi-Fi and other wireless type of operations inside of the vehicle need to be considered. It's also important to consider the test points that are included with these devices. How are we considering where to test, where to probe down to, how that's going to affect our measurement long term. All of that needs to be considered as we continue to develop these technologies.
Yeah, so I mean, we were talking about silicon carbide, and it comes in various different configurations. It could come in individual discrete devices. It can also come in modules as well, and that's what we're going to talk about here, how modules using silicon carbide can really improve efficiency in high power systems.
Well, that's a great intro to the trends. They're clearly much broader than perhaps our audience is aware of. And I know that Microchip has been involved in power for over 20 years. So before we address the when and why a customer might consider a module over a discrete, do you want to take a quick look at our portfolio of SiC products and solutions? Just give a brief overview before we dive into the details.
Yeah, Microchip offers a broad portfolio of silicon carbide products and solutions. We brand our products as SiC product portfolio, and it's a broad range of 700, 1200, 1700 volt, and 3.3 kV devices across bare die, silicon carbide diodes, silicon carbide MOSFETs, and silicon carbide gate drivers. And especially in the 1700 and 3.3 kilovolt class, it's becoming more and more ideal for a lot of these electrification applications where power fidelity and high current is constantly increasing. So we offer the broad portfolio to address the ever-increasing power fidelity of these applications. Please do bookmark, and this I want to make sure that you're able to find the resources at the end, microchip.com/SiC, and you can find everything you need there. I'll turn it back to my coworkers here to continue.
Yeah, so I mean, we were talking about how silicon carbide can improve the switching performance and how it compares to IGBTs. What we're going to talk a little bit more about and go into a lot more detail is how we can replace IGBTs in certain applications with silicon carbide and the vast improvements that it could make.
Okay, that's a great summary. Let's address when customers would want to use silicon carbide modules, and then we can get into the specifics of the demo. So why and when? Let's break that down.
So when you're optimizing your design, using silicon carbide, there's a few things you need to consider. One of them is the power density improvements that a module, especially with silicon carbide, could make. When you're at the very high power levels, 30, 50, 100 kilowatts and above, it really makes more sense to use a module with the integrated die than it does to have discrete devices. There are also advantages such as these modules are pre-tested, right, and they're designed for specific applications versus using discrete parts where you have to have multiple devices, multiple drivers, and that adds really to the complexity. Using modules will decrease your form factor, and a lot of times you talk about pricing and comparing prices to discrete versus module solutions. So with modules, you really have to look at the application and the power level and do a comparison. But many times in high power situations, you find that modules are the optimum device to be used.
So kind of what I'm hearing is that we have to acknowledge that one solution does not fit all, right? And the design must determine trade-offs. So when do we talk about when we say one module does not fit all?
Well, in terms of that, it's all about the topology aspect of that. And in terms of one aspect that does not fit all, it depends on your application. For example, here we show 3 examples, but there are dozens of other topologies that our modules could take on. If you're looking, for example, at a welding application, you want a simple phase link that you can parallel into 3-phase applications that address a particular welding or power supply or EV motor application. Or you may want a Type C type module for solar inverter, 3-phase inverter for unidirectional design. Or if you want multi-phase applications for PFC, bidirectional, for example, you might go for a triple Vienna rectifier with a power module. So there's many ways of going at it. Steve, have I missed any key points here?
No, in fact, let's take a look at the schematic on the right side of the slide. You can see this is for a triple phase leg Vienna rectifier. Now, if you were to implement this discretely, you would find that, especially in a higher power, you would have to use multiple devices in parallel. We have here 6 diode locations and 6 MOSFET locations. Using multiple die would mean, 12 to 18 discrete devices, whereas for right now, you could just use it in a single module.
So with dozens of topologies, that would lend itself to the need for flexibility and module customization, right?
Correct. So topology and specification is obviously an important factor in power designs. But also, once the module is settled on, what standard products that we offer should obviously be a starting point for our customers. Quite often, one size does not fit all, and there's a need to tweak or modify the module. So we do offer customization in the module, both substrate and base plate levels, so you can maximize the thermal conductivity between the levels to maximize the thermal throughput, protect the module to maximize performance and the longevity of the module. So you can balance that effect by mixing the substrate material against the right base plate material. And all this comes in our module topologies with optional PCB to terminate all the traces and the signaling. So it's a flexible customization scheme that is there if customers need it.
So we mentioned some comparison before between modules and discretes. And so we've got a pretty intensive breakdown here. You guys want to get into this?
Yeah, so if you look at the slide here, you see this is a module in a half-bridge configuration. And this is a 2 milliohm, 1200 volt module. If you look at implementing this in discrete packages, you'll find that you would need 36 individual packages to make the performance of one module. So each side has 18 devices. The high side would have 12 MOSFETs and 6 diodes, and the same with the low side. And if you look, this module also includes a temperature sensor, which wouldn't be included in the discrete design. So now, if you have discrete products on a printed circuit board, you have to make sure that your circuit board has enough capability for the current. You need to be aware of isolation and spacing on the board. You also have to be aware that the inductance, and we'll go more into that, the parasitic inductance of the package is much, much less. In this case, this module has about a 2.9 nanohenry inductance, whereas if you were to implement all of these discrete devices on a board, it would be more than 15 or 20 nanohenries. And later on in this demo, we'll show the importance of that.
Yeah, I think that 20 nanohenries in the discrete packaging kind of form factor is very optimistic, right? I mean, that can vary depending on the setup or the PCB layout that you've included, or just in the application, the space that you have available to you. So that's certainly very important to keep in mind. From a test perspective, evaluating each one of these individual FETs would certainly add its own challenge, right? And characterizing each one, whereas obviously the power module gives you much more of a concise individual test point that is available to you in both the bus bars and the square pins from a voltage test perspective. The other thing to highlight too is you've included the cost breakdown, which I think is really crucial. A lot of times it's considered that power modules are just sort of inherently more expensive than discrete solutions. But what should not be discounted is the labor costs that you've included. And labor costs, of course, includes the design and test perspective. And so, again, evaluating each one of those individual FETs and including its own parameters as a part of the test setup and characterization of the board that you're developing is going to take more time and is going to add additional cost and delay to a product realization.
So I heard inductance was an important factor. So let's talk about inductance real quick. What sets the SP6Li apart as a unique solution?
Well, our SP6Li modules, as Steve mentioned earlier, is designed very low inductance, so it maximizes your switching performance while minimizing your turn on and turn off switching losses. It's dedicated to silicon carbide technology, and that's why we're focused on the SP6Li low inductance module. It enables very high switching frequencies, as well as very high current capability that we can cover in a moment.
So if you look at the next slide, you'll see that we have a graph of overshoot versus drain current. If you have more inductance, you will have more overshoot in your switching. And taking a look at this graph, it compares a standard D3 type module, which is very common among IGBTs, versus the SP6Li module, which is an ideal package for our silicon carbide. And the reason is the switching speed. So if you look at an IGBT, it has a much slower switching speed than the silicon carbide. And that lower DIDT allows it to be compatible with higher leakage inductance modules. When you switch as fast as a silicon carbide device does, what you will get is overshoot in your voltage. And this adds excessive voltage stress to your module. For example, this is a 900 volt bus. If you were switching 250 amps with a typical IGBT speed, you would see about, you would see about 1200 volts of overshoot, of total voltage, which is about 300 volts of overshoot. But with silicon carbide in an SP6Li module, you're only looking at about 1050 volts, or about 150 volts of overshoot. So the other benefit is the efficiency across a wider working voltage range. So if you look at, again, switching losses versus the drain current in this graph, at 10 kilohertz with a D3 module, and it's about 20 nanohenries of inductance, you can see there's about 100 watts of loss with a typical switching frequency. And with the SP6Li module, you can see there's a little bit less. But as you increase the switching frequency to 25 and even to 50 kilohertz, you can see the gap in switching losses widen. And because we're using modules at very high currents and high voltages, this is where you get a significant advantage using a lower inductance module like the SP6Li.
Great, that's two great points on technical aspect of low inductance. And then number three is all about price. Obviously, we covered earlier that on the board level how using module could potentially save customers money, especially through the qualification and characterization cycle time that the manpower put into the design. On the other end of the spectrum, our customers and their end customers care about what can they save in terms of energy usage, for example. What bill are they going to receive at the end of the day? But this example, we look at an average of 23 cents per kilowatt hours of per unit cost. Now, your local cost may vary, so this is a rough estimate. And using a module, each SP6Li module that Steve outlined earlier could potentially save the end customer up to $3,000 per year based on our analysis. So that's significant. That's each module times however number of modules per platform used in our system. That can save in upwards of several tens of thousands of dollars or more in energy bills for the customer. And that's significant for end application usage.
So that's a great explanation of the benefit of low inductance silicon carbide power modules like the SP6Li. Let's talk about hardware. What kind of hardware is available to support the characterization and evaluation of this module?
So we have developed a SP6Li double pulse test board. And we'll go into what double pulse test is and how it benefits the knowledge and availability of information for how well these devices can perform. If this board over here has the ability to look at high currents and high voltages for our switching modules.
Yeah, so you can see this is the basic layout of our double pulse evaluation board. It's got our supply voltages coming in up at the top here, a bank of different types of capacitors being utilized, a gate driver board down here at the bottom, and then various test points that we'll get to in a little bit, all with an air core inductor being used on this side.
So I heard double pulse testing mentioned more than once. You want to dive deeper on what double pulse testing is?
Sure. Yeah, double pulse testing is a very significant test. It's been around for a long time, but it's had quite a resurgence, again, with the a proliferation of wide bandgap topologies. The basic premise of double pulse testing is to produce several pulses, usually at least two at the gate, generally the low side gate in this particular half bridge configuration you see here. And with that double pulse, you're looking to stress the component and evaluate any sort of thermal considerations or energy dissipation considerations that need to be accounted for. So again, the general setup is in this half bridge configuration, you typically utilize an inductive load to simulate a real world type of load in the native environment of the device. You use a power supply to charge up the bank of capacitors that we saw on the board. And then you supply two different pulses of varying widths to the low side FET. That first pulse is meant to energize and load the load inductor or charge up the load inductor with the desired load current, again, for a given application. The turn off of that first pulse then puts the high side FET into a freewheeling mode of operation where the current flows through the inductor and the body diode of the high side FET. When the low side FET is then pulsed again, that current is then allowed to flow back through the FET and out through the load inductor, and usually causes a fairly significant spike that needs to be accounted for. And that power dissipation is what we call generally energy on, and needs to be considered for thermal considerations and other characteristics of the device under test.
And then, of course, there's switching loss.
So let's go through some switching loss examples. In this case, you can see on the slide that we're looking at a turn-off event. Now, power occurs when you have voltage and current at the same time, right? And when you turn off a device, you have both voltage and current appearing across the MOSFET simultaneously. If you look at how the switching event, this turn-off, occurs, as you lower the gate to source voltage, which is controlling the MOSFET, you'll see that at some point you start to increase the voltage across the drain to source of the MOSFET. But at this time, drain current is still flowing, and so now you have some power. The area under that triangular purple shaded part of the waveform is the actual energy that's dissipated during this event. So you can see that as the gate voltage continues to fall, that you'll see the current start to go down. At the end of the event, which is at time TB, then the voltage is being blocked by the MOSFET, but there's no current flowing, and therefore there's no more energy. You can calculate the energy by looking at the area under that triangle. It's a good estimation of how to calculate that. And then depending upon your switching frequency, you can now calculate the power being dissipated in the MOSFET due to this turn-off event. And so the total switching energy or power that's being dissipated is the sum of this turn-off event plus the turn-on event, and then any losses due to conduction during the switching cycle.
So where should switching parameters be calculated?
Yeah, this gets to several of the challenges that we work through with double pulse testing. One recent or relatively recent change is that certain standards bodies like the JEDEC and IEC community have implemented specific standards that indicate where silicon carbide and other wide bandgap materials should make this particular measurement. So for instance, this particular IEC standard is specified for the energy on and energy off calculation for silicon carbide devices specifically. And what you'll notice is in the graphic there, this is showing the energy on, or this is the turn on event indicated by the second pulse in our double pulse example. So energy on and its gating factors are indicated between the 10% rise point of ID and the 10% fall point of VDS. And all of that indicates where the specific energy or that integral under the curve that Steve was just mentioning should be calculated. Now, this is sometimes a relatively challenging measurement to make simply because of the gating factor. There are sort of tricks that can be made in terms of exporting the waveforms and doing some post-process analyses. But if you wanted to make this measurement in real time, at minimum it would require some clever tricks in terms of gating, using some cursors or timing parameters for each measurement. So what we'll show in our demonstration is this calculation can be made in real time with some measurement tools and algorithms that we've utilized on our oscilloscopes.
So it sounds like there might be some other challenges to be aware of.
Yes, yeah, another really common challenge, especially in double pulse, in particular with wide bandgap materials, is as we switch these devices harder or faster, the common mode interference that is caused, particularly on the high side FET, becomes more evident. So take, for example, this example with a typical setup using some of the SP6LI type of supply voltages. So if we had a supply voltage being provided to the module of 1200 volts and a typical gate signal of 25 or 20 volts is attempted to be measured on the high side FET, a typical high voltage differential probe at the switching frequencies and the dVdTs that are required for many of these gate drive signals is subpar. And so subsequently you can see that in this example, 26 dB of common mode rejection gives us roughly 60 volts of common mode error. And so you can imagine looking at a 20 volt signal with 60 volts of error is very, very challenging to see. What we've developed as a solution to that is an isolated differential probe that provides galvanic isolation from the probe head back to the connection on the scope. It utilizes MMCX connections down to the device, which provides some extra shielding and a very solid connection down to the board under test. And ultimately that gives us 100 dB of common mode rejection at the same 100 megahertz of bandwidth. And so you can see the drastic reduction now down to 12 millivolts of common mode errors present here in this example.
So that concludes our discussion portion. I think it's time to get on to the demo. We've got some equipment here that we want to focus on. So let's get to it. Cameron and Steve, do you want to break down what we're about to see here?
Sure. So the setup that we have with the double pulse demo board that Microchip has developed utilizes some test equipment from us, including our 5 series MSO, our AFG 31000 as a function generator, and then a number of different probes that you can see over the top of the demo board here. So we have for VDS measurements, we're utilizing our high voltage differential probes. We call it the THDP 0200. It is a 1.5 kilovolt differential probe at 200 megahertz of bandwidth. For current, we're using a 600 amp Rogowski coil, and you can see the connection down on the board here. For gate measurements, we're going to be comparing 2 different probes. One being, again, the traditional differential probe, our THDP 0200, and our isolated differential probe, what we call our TIVP1, which is 1 gigahertz isolated differential probe, again with the MMCX connection that you can see here. We should also note that Steve and I went through the de-skewing process of all of these probes prior to setup and prior to connecting down to the board here. So now we're going to transition over to the demonstration on the oscilloscope. So for this demonstration, what we'll show on the scope screen is we've got a number of different measurements set up for the different channels that we have kind of pre-configured. We've got VDS voltages measured on channel 1, our IDS measured on channel 2, and then we'll show the comparison of the gate voltages on channel 3 and 4 here, again comparing the isolated and non-isolated differential probe. If we look at our measurements, this provides a really clever way to set up where the calculation of energy on in this particular example should be made. So we'll provide the GUI here the maximum voltage that we are going to be seeing. In this case, our supply voltage is 600 volts, and the maximum current that we expect out of the SP6LI module, which in this case is 300 amps. The gate voltage here is 25 volts, and our first pulse width is 15 microseconds. All of this helps the oscilloscope set up essentially kind of an auto set function where the voltage and vertical and horizontal settings of the oscilloscope are all pre-configured appropriately. We can also pre-configure the function generator to set up the varying pulse widths that we want supplied to the low side gate. In this case, we're supplying a 0 to 5 volt signal into a high Z load with, again, the first pulse of 15 microseconds, charging up that load inductor, a small gap between the second pulse, and then a short pulse, again, kind of re-energizing the low side circuitry. This is all remotely controlling the function generator over a LAN style connection, which we can see here. So the scope and its GUI will actually remotely operate the AFG for us. Once we have this all set up, we can then energize our supply voltage and our power supply and simply hit gate stimulus. And that will trigger the function generator to supply those two pulses and trigger the oscilloscope to take a single acquisition. And this is the resulting waveform on screen that you see here. So Steve, what do you see so far from an acquisition standpoint? How did we do?
So it looks very, very good. And I wanted to just comment a little bit about how we picked the 50 microseconds and the 2 microseconds. If you look at the blue trace on the waveform here, that's the drain current. And because there's a certain inductance that is in series, between the power supply and the MOSFET, the longer that you take to charge up the inductor, of course, the higher the current. And this is how you set the current for the test, right? If we wanted more than 300 amps, we would just extend that 50 microsecond time. If we wanted lower current, we would make it shorter. Also notice that there's a fairly small amount of time between the first pulse and the second pulse, because when you are freewheeling during the off time, you're freewheeling through the diode, as you had explained before, you lose some of the energy in the inductance, and that will reduce the current. So really you want to make the interval between the first and second pulses as short as possible. You want to make sure the ringing has died down and then provide that second pulse. The other thing that I see interesting here, Cameron, is looking at the gate pulses. The green trace seems pretty much noise-free compared to the red trace. Can you explain what the difference is?
Sure. Yeah. So this is comparing the gate to source voltage, again on the low side FET, for using two different styles of probes. So essentially, at the same test point, we're comparing two different probes. One being our THDPO200, kind of the traditional differential probe used for high voltage measurements, and then our TIVP, this is the isolated differential probe in green. So what you're seeing here in the difference in ringing and amplitude of that ringing in this particular case is that common mode coupling that you see that's being coupled into our differential probe, and well, better said, is not being rejected by the common mode rejection of the differential amplifier of the probe, whereas the green trace is doing a much better job at these type of switching rates. So that's what you see differentiating these two. What I want to point out is, again, this is all measurement from the low side FET. This example would be even more extreme if we were probing the high side FET and characterizing it in this double pulse example. So if we want to dive into the measurements and their results, note that the energy on measurement and all of the other double pulse measurements that you see along the right-hand side are now pre-populated. So if we single click on our energy measurement and single click onto this particular badge, you'll notice that we've zoomed in on the turn on pulse of the second event. So in this case, take note of the green cursors that you see down here on the orange math waveform trace, those are actually showing the 10% fall point of VDS and 10% rise point of IDS as the start and stop parameters for which that integral under this power curve is calculated. And so, Steve, we're getting a couple of results as well pre-populated here for energy on and energy off. Do you want to talk about whether these are to be expected for this particular module?
Yeah, so if you look at the turn-on energy, you're reading about 7.5 millijoules. The turn-off energy is probably about half of that. Sometimes people ask why the turn-on energy is a little bit higher, and that's due to the reverse recovery and also the output capacitance. When you turn the MOSFET on, current just previous to that event is freewheeling through the diode. When the diode is reverse biased in order to block, some of the energy that's in that diode is now dissipated within the MOSFET, the low side MOSFET. Also, when you turn on the MOSFET, any capacitance in the output, that energy is also dissipated within the MOSFET during the switching event. And so you will usually get a higher turn-on loss than you will for a turn-off loss.
Great, thanks. Yeah, and one more thing to point out on the measurements. So we indicate a single shot measurement per acquisition, both in the measurement badges around the right-hand side, but also within this results table that you see I've pulled up at the bottom here. This table can be exported into an Excel file for further analysis, and it gives you both the statistical measurements on a single shot basis, but also a cumulative basis. The statistics that you see on the right-hand side of the table over here, if we were to take multiple acquisitions and say, for example, vary this, this particular board or module over temperature or over time or different load conditions, these cumulative statistics would tell us how that change is occurring. And so now we're getting both dynamic and static measurement characteristics of our device. So these are just some of the measurements that we can make with our wide bandgap double pulse measurement suite that we have built into our 5 series oscilloscope. And again, the whole goal is to help you characterize your device in circuit in real time to get to market faster.
Well, very compelling demo, gentlemen. Thank you very much.
Thank you.
At this time, let's get to our Q&A. So let's go to Allison and see what kind of chatter we're seeing in the feeds. Allison, what kinds of questions are we receiving from our online audience?
We do have a handful of questions for you guys. We'll get started with this one. It's coming from LinkedIn. They would like to know, how do you achieve that small module stray inductances? Do you have decoupling capacitors inside the module, or is it a more intelligent way of packaging than the other power modules you can find nowadays in the market?
So when we designed the SP6LI module, it was designed with fast switching in mind. There are no internal capacitors within the module. In many cases, that actually presents a reliability issue, since the temperatures inside the modules can be fairly high. What we did is the layout of the module, the way the connections are made and the way the die are put into the device is conducive towards a much lower leakage inductance.
Thank you. We'll move on to this next question. How much bandwidth should be considered when using scope probes for making measurements on this SP6LI MSiC module?
Yeah, so bandwidth for high-powered switching applications, such as our double pulse example, are less to deal with the switching speed of the device and have much greater dependency on the slew rate or the rise and fall time of the power signals on screen. And so from a bandwidth consideration, we need to consider mostly the rise and fall time of the gate signal, as that is a huge driver in that fast DVDT that we're looking for. So typical rise times for power modules like the SP6LI are in the tens or single digits nanoseconds type of range. And again, that relates back to roughly, several megahertz or tens of megahertz in bandwidth. Our general rule of thumb is that we want a rise time that is 5 times smaller than the fastest rise time that you anticipate measuring in a power signal like this. So generally speaking, for the types of rise and fall times that we're looking at for the SP6LI, we'd be looking at hundreds of megahertz in bandwidth from both a probe and from a oscilloscope bandwidth perspective.
Thank you. This next question here asks, what considerations, if any, should be given to using single-ended probes in double pulse measurements?
So in general, single-ended probes are much better in terms of their DC gain accuracy relative to high voltage differential probes. They also tend to be less expensive than differential probes. So it is possible to use them in double pulse testing. The one very critical consideration that needs to be kept in mind is they should only be used in reference to the low side FET, as that low side FET can be ground referenced. And that second point is ensuring that the ground on the low side FET is indeed referenced back to a stable ground. We've seen examples where certain ground bounds that gets introduced with devices or with demonstration boards or that gets picked up along the way, coupling back to the chassis ground of the oscilloscope, all sort of cause more common mode interference with the surrounding devices and the measurements than is desired. So in general, single-ended probes can be considered for low side gate measurements, but in, I would say, most applications, I see differential probes being used for that floating aspect that they provide.
Great, thank you so much for answering that one. We do have a couple more here. I'll go to this next one. At what power level should you consider using SiC modules over SiC discretes?
Yeah, typically, I'll take that one, please. Typically, what we're seeing in the module transition is in around the 30 to 50 kilowatt range. Now, it's not set in stone. You can obviously go lower in the power rating, but that's a typical range where the complexity of paralleling discretes comes to a pain point where using modules in a smaller footprint will come into play. So that's about the rough range of 30 to kilowatt range. Thank
you. We'll move on to the next one here. Why is the low inductance characteristic in Microchip's SP6LI SiC module important in high current, high power designs?
So it's not just the inductance within the module, it's the overall system inductance, including the bus. If you look at, for example, the way we designed the SP6LI double pulse test board, we start off where the power comes in, we start off with some high capacitance bulk capacitors, and then we move on to some film capacitors here, which have a much lower inductance, parasitic inductance within these packages. And then underneath the board, we have smaller capacitors that are much lower inductance than that. So in doing this design, we were trying to minimize the bus inductance going to this module using this board. And that's what systems that are using silicon carbide should do. A lot of times we take IGBT design and we just drop in silicon carbide and wonder why it's ringing so much. And that's due to not just the package parasitic inductance, but also the board and the system inductance as well. And the reason it's so important is because the more inductance you have, especially when you're switching high currents very quickly, is that you get a lot of voltage ringing. And that excessive voltage ringing can cause some reliability issues, especially if you overshoot above the voltage breakdown of the device, and EMI issues as well. So if you have a lot of ringing, you're going to have some issues with both conducted and radiated emissions.
Thank you so much. Alrighty, the next question here. Why are silicon carbide products, in particular SiC modules like SP6LI, attractive for use in electrification applications that have been dominated by discrete Si and Si IGBT module solutions?
I'll take that, please. Yeah, typically, as you know, going from silicon to silicon carbide technology, designers will notice the increase in efficiency and performance, switching frequency and increase, enabling much higher performance and efficiency in the device. And also, while at higher thermals, typically silicon carbide can tolerate our devices, for example, rated up to 175 degrees Celsius in operation. So the higher thermals also enable performance operation at higher temperature range. In addition, due to the efficiency of silicon carbide over silicon, the designs enable much smaller magnetics can be used. The system can run potentially cooler. All that translating to a much smaller, compact platform that a customer can deliver. Typically, maybe 20, 30, up to 40% smaller platforms than silicon solutions. Now, on that front, that's the silicon to silicon carbide transition. We focus on modules today, primarily because silicon carbide modules also enable an even more compact footprint. You have all the die and qualifications packed into a single module, for example, whereas as Steve mentioned earlier in the broadcast, that potentially one module you would require up to 24 parallel silicon carbide devices. So that's significant real estate there that you wouldn't necessarily need for a single module in comparison, and in particular low inductance like our SP6LI module. And then at the cost level, obviously, you're looking at comparable costs of modules on silicon carbide discretes and modules, but the time involved, the resources involved for qualification can be significant when you're trying to figure out the parallel discrete devices versus potentially a pre-qualified data sheet module that a vendor like Microchip would deliver to the customer.
Thanks, Jason. This next question is wondering, do you have simulation models for SP6LI MSiC modules?
So Microchip uses Plex as a simulation tool. We have models for our modules developed using Plex. And if you as a customer have that tool, we can provide those modules. If you don't have that tool, we have an online version of the Plex simulation tool that you can get off of our website, microchip.com/SiC. And this allows anybody to do simulations of multiple topologies using not only our discretes, but also our modules as well. One of the advantages of using Plex is that it uses actual data, and that data is taken from double pulse test setups like the ones we showed to you today. This ensures that the test data and the model are coordinated so that the model gives you the most accurate simulation information that we can provide.
Thank you. And we have one more question. What are several benefits and disadvantages for using DPT to characterize SP6LI MSiC module switching characteristics?
So I don't want to call it an advantage, but one of the things you have to consider is that when you're testing a single module, then you're getting the data from that module. And it doesn't really account for part-to-part variation, which means that you have to do a large number of modules in order to get a complete set of data. But this information that you're getting is the actual measured data in a system. And so therefore it's going to be the most accurate that you can get compared to just running a SPICE simulation.
Yeah, I would echo that system level data. I mean, oftentimes, data sheets can provide information about the performance of the device, but all of the parasitics that get introduced once you plug the board, once you plug the module down onto the PCB board and attach the different loading devices, that all will affect your performance of the silicon carbide module. So having system level detail of real world performance once all of the parasitics and other devices that are included within the subsystem is really important from a testing perspective. The other thing I would mention is since double pulse testing is a single shot type of test, oftentimes it's necessary to test and evaluate the device over a variety of different conditions. That can be temperature, that can be loading conditions, that can be interference with other type of common mode sources, and then again, evaluating the real world performance that you have. So I would argue double pulse testing gives you a better representation of how your product is going to fare once the other parasites and other conditions are accounted for.
Thank you guys so much for answering these questions. That'll wrap it up for now. If we have a question that we were unable to get to, please feel free to leave it in the chat and someone will try to get back to you, or you can email us at livestream@microchip.com. Thanks again for your participation, and I'll turn it back over to Dana.
Thanks, Allison. For more information on the technologies featured in today's live stream, you can scan the QR codes in the middle of the screen, or if you're on a desktop, you can also head over to the web at microchip.com/SiC or tektronix.com. That wraps up today's edition of Microchip Live. Thank you to our distinguished panelists for a great discussion, and thank you to every one of you out there for joining us live. Have a great day.